Welcome to the demo of an early prototyping tool for Car2X systems. This tool was created by integrating a scenario-based MDE process for dynamic topology collaborative reactive systems with the driving simulation software OpenDS. We will present a brief overview of the tool and show an example of its application. Dynamic topology reactive systems are systems of distributed reactive components, where the relationships between these components can change at runtime, for example, due to the movement of the components. These changing relationships usually influence the behavior of the components that must fulfill context-specific responsibilities. Examples of such kind of system are Car2X systems and reconfigurable production systems. The design of a dynamic topology reactive system can be a complex challenge, not only due to the dynamic topology, but also because of the distributed and concurrent nature of their software, and because they often control complex physical and mechanical processes. Finally, the systems are often safety critical, and therefore extra rigor is required during design. Modeling such scenarios using traditional approaches ends up being too complex and confusing to understand. To address this challenge, we developed a formal scenario-based design approach for dynamic topology reactive systems. It is based on the scenario modeling language SML, an extended textual variant of life sequence charts. With SML, context and specific requirements and environment assumptions can be specified as a set of separate guarantee and assumption scenarios that form a scenario-based assumed guarantee specification. Like, for example, this guarantee scenario, where we model the behavior of a car in the system when it approaches an obstacle. Or in this assumption scenario, where we model the behavior of a driver as we expect he will not enter the narrow passage without receiving a positive or negative signal. This approach has several advantages. First, the scenarios are aligned with how humans conceive and communicate requirements during the early design. Second, they have a formal semantics and can be formally analyzed for inconsistencies. Third, they can be executed via the playout algorithm, which makes it possible to use them for simulation or even as code for the final system. Consider the following example scenario from a Car2X driver assistance system for safely coordinating cars passing an obstacle. The blue dotted line represents a particular position or marker placed on the road, which can be detected by cars. When a car passes this position, it detects that it is approaching an obstacle. We now require that when a car approaches the obstacle, it must register itself at the obstacle controller. The obstacle controller will then check if there is any other car registered for passing the obstacle from the other side. If yes, the first car is not allowed to pass the obstacle and is added to a waiting list. If no, the obstacle registers the car and allows it to pass. Several such scenarios can occur in the system at the same time. With the scenario modeling language, such scenarios can be modeled formally, and, due to their executable semantics, these scenarios can even be used as the implementation of the system. We created a scenario-based design process, SBDP, to compile executable code from SML scenarios, which works as follows. The first step is to model the SML specification, which consists of a set of assumption and guarantee scenarios. Then, this specification can be formally analyzed for inconsistencies and whether the execution can lead to violations. If all checks are successful, the SML to SBP compiler generates then scenario-based programming code. This code is for a specific Java framework that we developed, where scenarios can be coded as special threads. They interact by blocking and triggering one another. Last, code must be added to bridge problem-specific events in the specification to platform-specific events. For example, the car's position events, modeled in our specification as car approaches the obstacle as we showed previously. They may, in the final system, be derived from GPS sensor data or from sensors that detect markers on the road. The SBP code can be deployed on a single node or in the distributed setting. The distributed setting works via a naive approach that copies the complete code to each node in the system. Each node then has a specific setting defining which software components in the system a particular node represents. At runtime, all nodes synchronize on every event in the system via the network, which guarantees that all nodes' execution states are kept consistent. This distributed execution technique is yet a naive prototype, but is already possible in principle to derive software for the Car2X driver assistance system this way. However, instead of running the code on real cars, we integrate it with an interactive 3D driving simulator. Our virtual prototyping system works as follows. A multi-user driving simulation with OpenDS runs on 2 PCs. Android devices are placed next to the screens. These Android devices represent the car's dashboards. And they also execute the scenario-based program code that would run on the cars. The laptop represents a computing node of the road infrastructure. It executes the scenario-based program code of the obstacle controller. The system is distributed and exchanges messages via the MQTT protocol, an open message protocol for machine-to-machine communication. A simulation run may work as follows. For example, assume that in the 3D simulation, a car approaches an obstacle. This event is created when a car collides with a corresponding object that represents the corresponding position marker. In this case, the position marker is this red line on the screen. The collision event is mapped to a specification level event, for example, approach an obstacle, which is then shared with all other SBDP components in the network. Specification events that require to show stop or go signals to the drivers are implemented on the Android devices in such a way that simply stop or go labels are shown on the screen. For more information on the technical details, have a look at the related videos and publications linked below the video. Thanks for watching, and let's take a look at the system in action now.